Okay, so to take a running start at today's first time at applying the ideal gas law equation, of course, this doesn't look like the ideal gas law equation, but remember that we got to this in your notes because, I just think this is so cool, for any gas, and I usually draw a little box and show my little gas particles bouncing against the side of that box, you know, creating pressure. Okay, for any gas, and those little particles are gas particles, you really know all you need to know if you have all of that stuff about the gas. Okay, and actually you can use, we looked at Boyle's law that relates volume and pressure, and then we looked at Charles' law that relates volume and temperature, and Avogadro's law relates number of moles and volume. So actually, with a joint proportionality, you can come up with this relationship between these four variables, that they all are some constant in our universe anyway, if they're behaving ideally. So thus, actually, we can flatten it out. That equation you saw in the previous slide, if you flatten it out, this is actually what the same equation. So PV is equal to nRT, where R is the ideal gas law constant. And again, this is assuming that a gas is behaving ideally. Those two assumptions, and actually the third part in Unit 5, we're going to talk about gases that aren't behaving ideally, but that they actually they have no intermolecular. They aren't connected at all to each other. They have no interaction with each other, and that their volume of the particles is basically zero compared to the volume of the container they're bouncing around in. So in physical science, it's all about units. Units are very important. It's called dimensional analysis of working problems. So actually, if we go ahead and use pressure in units of atmospheres and volume, which pressure, that's the biggest one, because actually I've seen R, a value for R, when pressure is in millimeters of mercury instead of units of atmospheres. But if pressure is in atmospheres, volume is always in liters. Of course, N, the variable N, is the number of moles in moles. T, temperature, we talked about before break, actually has to be on that scale where the absolute zero really is a player. So it's the Kelvin scale. Then actually value for R, and you're probably going to want to put this on your note card. Let's see, did I say you can bring a whole sheet? Okay. Like if I was like really into this or whatever, I like the way things feel. So I would get like a piece of cardboard or something, you know, some thick construction paper and make my note card out of that. Or just a piece of paper, same thing. But if you're into aesthetics, you know. So I would go ahead and put this value of R on your sheet to bring with you to the final. So again, as long as units of pressure are in atmospheres, then R takes on a value of 0.028058, but the units are important, okay? Units of R then would be liters, atmospheres in the numerator, mole and Kelvin in the denominator. That's the units of R. So on your final, if you have a gas law problem to write out, you know, you're going to have to include all units. And so R actually has these units. And I'll show you how the units cancel out and everything. So it's all wonderful. So let's work a problem, okay? And for I think if I did these very often, I probably would get away from this convention, because actually I was working some hints for your homework at the end of this part that's going to be due on Friday. And I'm like, this gets old, drawing these little boxes. So I don't know. Okay, so there's my little gas of interest. And usually, I know it's a gas law problem, so I'll probably know that I'm going to be using the ideal gas law equation. And somewhere in there, I'm going to have, of those four variables, somewhere in there, one of them is going to be a question mark, basically. So on the next page, the next few slides, I actually have builds to work this. But, of course, pressure is 732 millimeters of mercury, but notice that you're going to have to convert that to atmospheres. Okay, and a slide coming up, there's an exact relationship between those two pressures, and the number is the number is 760. So 1 atmosphere is exactly equal to 760 millimeters of mercury. And volume here, oh goodness, see, volume, question mark. Number of moles, oftentimes this is the case. Notice I'm not given moles, but I'm given the 0.20 grams, and I can get to moles because I know the identity. I know this is CO2 gas, okay, so I can use the molar mass of CO2 to get to moles. And of course the temperature is given. We have a little conversion needs to go on there too, because it's, as is usually the case, it's given in Celsius, and you got to get it to Kelvin. So we have a couple of things on the front end, okay, 3 things on the front end, and then knockout volume. Okay, so it looks like this then. So PV is equal to nRT. We just got to be careful about solving for, we got to be careful about our algebra. Okay? So what I would do then is multiply both sides by, what, 1 over P. That makes sense? Because then I get V by itself. Okay? So however you learned that, and it's very easy to make a mistake. If you make a mistake in rearranging this and you start plugging things in for your variables, if it's wrong, your units are going to scream it's wrong because your units are not going to cancel. So once we convert our grams to moles, and once we fix our temperature from Celsius to Kelvin, and once we fix our pressure from millimeters of mercury to atmosphere, we're going to plug into this. Okay. So yeah, I would go ahead and throw this on your note card. In my notes even, I think that last digit, instead of the 0.08205.8, sometimes I have 0.082057. I don't know. But it's always liters, atmospheres per mole Kelvin. So let's go ahead and kind of clean up what we need to clean up. So this slide knocks out the whole getting from grams of CO2 to moles of CO2 using what we talked about before, periodic table for carbon and oxygen, okay, getting the molar mass of CO2, using it as a conversion factor, rounding it to 2 significant figures, okay, that's here to stay. So we have 2 significant figures in the mass, so we're allowed 2 in the number of moles. Okay, and then this is correcting the temperature from Celsius to Kelvin. Remember, in this case, we add 273.15. Sometimes if the Celsius temperature we want to convert is to the nearest 1 anyway, if you add 273, it's the same thing as adding 273.15, because it, remember, since we're adding, we round according to decimals. In this case, it's 1 decimal. In that case, it would be to the ones place. Okay, so that's going to be our T. And then down here is fixing what I call the pressure term, since it was given in millimeters of mercury, and the R value we're using is in units pressure of atmospheres. There's an exact relationship between millimeters of mercury and atmospheres. So your lab next Thursday is a good one. It's a gas lab. And yes, Thursday is the day right before your final. So what I'm going to do is you will get lab credit by, I can't remember, I'll give you more details, but basically you're going to complete the calculations in lab and get lab credit for gas lab next Thursday. Okay, so that's going to be our P term. Ready to plug and chug. But in plugging and chugging, thou shalt not have any naked numbers. So volume, in the top we have 3 terms, the number of moles, the N, the R, and the T. Those are all in the numerator. So the units of N, of course, are moles. The units of R, that middle term in the numerator, is liters, atmospheres per mole Kelvin. And then, of course, we have our temperature term in units of Kelvin. And then there's only 1 term in the denominator, the pressure term. And that's that 0.963 atmospheres. So it looks like we are only allowed 2 significant figures because actually the limiting term is the number of moles. So round it to 2 significant figures. I want to show you, it's 0.11, but I want to show you how the units we get are right. Okay, so looking at the numerator, we have units of moles in the first term, and then units of moles in the denominator of the numerator. So those cancel. Okay, looks like atmospheres cancel. Atmospheres in the numerator of the numerator cancel with atmospheres in the numerator of the denominator. They cancel. Looks like Kelvin cancel. Okay, and so, yep, all we're left with are units of liters. That's it. That's the answer. Okay, any questions about that one? Very good. So let's do another problem. And in this one, actually, density. It's funny because when we look at density of liquids and density of solids, it was always grams per mil, or grams per cubic centimeter. But gases occupy a larger volume, so oftentimes the volume term is not milliliters or cubic centimeters, it's liters. So a good way to describe density, mass density of a gas would be grams per liters. So this problem is a little bit different. I'll go ahead and kind of in the vein of your homework coming up, I draw my box. Okay, we know that's argon. Sometimes you don't always know the identity of the gas. Okay, and then I write P, V, N, and T. Okay, and notice that we're given the temperature of 25 degrees Celsius. Of course, we better get that to Kelvin. And we don't have to fix our pressure term because it's already atmospheres. Now, in this case, and the hint was given, kind of, I guess you'd call it a hint, but notice we don't want to take it all the way to volume. We don't want to take it all the way to liters, and we don't want to take it all the way to number of moles. Okay, we want to actually, oh, I know. Now I remember. Do you see where we aren't given the volume and we aren't given the number of moles? But if you go ahead and calculate moles per liter, which is the molar density, okay, that actually we are one step away from grams per liter. What you're supposed to be finding is grams per liter. But if you have moles per liter, do you see where you can just use the molar mass of argon since you, of argon since you know what its identity? And voila, mm of argon. And actually that's how we're going to work this. I don't know if that made sense. So let's go ahead and knock this out. Ideal gas law equation, but instead of solving for one variable, we're going to leave a pair of variables, a ratio of variables on one side, that being n to v. Okay? So if you solve for n over v, you divide both sides by v and move the RT over. Okay? Actually, this is the same, the ideal gas law equation rearranged, solving for what's one step away from getting the grams per liter. This is moles per liter. And we're close to this, right? All we got to do is fix the temperature term. Now let's go ahead and plug in. Okay. So again, we can get from this molar density to the mass density using the molar mass, which we know for argon. We just have to use a periodic table. So there again, restating the pressure of 1.22 atmospheres, that's good to go. The temperature, we need to add 273 to it to get 298 Kelvin. So plugging in and making sure we have our units as they should be. let's take a look at how things cancel. In the numerator, we had 1.22 atmospheres. Notice that atmospheres in the numerator will cancel with units of atmospheres in the ideal gas law constant in the denominator, in the numerator of the denominator. And then also in the denominator unit-wise, our kelvins are going to cancel. And looks like we actually have only units in the denominator. So units in the denominator are liters per mole. If you take anything from the denominator and simplify it, or it's actually take it out and switch it over. So actually that's units of moles per liter. And notice that we need to round to 3 significant figures because we're limited by both the pressure and the temperature. So we're not quite done. But now if we go ahead and use the periodic table looking at the molar mass for argon, we can go ahead and have moles cancel and be left with grams. Okay, so the decimal number for argon is 39.95. So 39.95 grams per mole. We plug it in that way to be left with what we're trying to get to, which is grams per liter. Rounding it to 3 sig figs, that's your answer, 1.99 grams per liter. Can't remember what I said next. Okay. So I always think of like the gas additive, STP, when I get to this part, but STP in gases stands for standard temperature and pressure. And as I said when we talked about thermodynamic problems, the standard conditions for both of those types of problems are different. So the standard conditions for gases are 0 Celsius and 1 atmosphere. Standard temperature is 0 degrees Celsius, which is 273.15 Kelvin, and a pressure of 1 atmosphere. So there's this kind of neat thing that happens. I guess it's not really that neat. But some of you may have memorized this 22.414 liters, okay, at standard temperature and pressure. And all that is basically looking at the ideal gas law equation and saying, by golly, if I have 1 mole of gas, any gas, I don't care what the identity is, okay, and if that gas is at standard temperature of 273.15 Kelvin, standard pressure of 1 atmosphere, then by golly, the volume is set in stone, 22.414 liters. And I'm going to circle that because actually on Friday when we come back and work, I think it'll be Friday, yeah, when we come back and work a stoichiometry problem, we're going to make use of this relationship. Basically, regardless of the identity of the gas, and as long as it's at what's, for gases, a standard temperature and pressure, you can count on 22.414 liters being the volume that 1 mole will occupy. All right. So the last thing to talk about is this combined or general gas law, or laws, okay? The most common one is the one in which the number of moles is held constant. So we'll take a look at that, okay? The number of moles is held constant. Well, if your number of moles or N is held constant, actually you can throw it over with the R term, okay? So if R is constant and now N is constant, okay, then actually the only thing that's varying is these. What I haven't said, and you're going to see here in a minute, it's going to come screaming through. Basically, these are great if you have what I call state 1 and state 2. State 1 and state 2 simply means that you're going to have the number of moles, N is going to be constant. Basically, it's held in a container, and you're not going to let any of those gas particles out. That's it. The thing that you're going to let fluctuate perhaps all three things you're going to let fluctuate. That leaves the pressure, the volume, and the temperature. Have at it. Okay, but your number of moles are not going to change. It happens all the time. We can find a gas and don't let it out, but some other things can happen with regard to those other variables. Well, then, if PV over T is equal to a constant, then we can come up with this kind of cool thing between state 1 and state 2. Okay, so that you've combined your gas, you're going to allow the pressure to change, the volume to change, or the temperature to change between your state 1 and state 2. When dust finally settles, these relationships of the two states need to be the same. That's all that is. Okay, so we'll take a look at one. And these, you know, if you haven't done many of them, they don't take too long to kind of get the hang of it. But what I've been doing, see, my boxes are getting uglier and uglier. You know, what I've been doing is basically identifying, that should be V2, T2. Okay, you identify for state 1 and state 2 the three things for both of them. So on the next slide, you're going to see these pulled out. So when you see the word originally, that would be state 1. Okay, change 2, that would be state 2. So sometimes if you're like me, story problems like this, I kind of have to kind of go back and forth and kind of concentrate. So from that paragraph, you can pull out these things. The initial pressure, volume, and temperature are this. So I'll go ahead and mark this, but it'll kind of leave from my slide. What you're going to see with this sort of problem is you can leave the pressure and the volume in any units as long as they're the same between your two states. It's a wonderful thing. I love these because if you're like me, I hate going back and forth between millimeters of mercury and atmospheres. And, okay, any units as long as they're the same. Temperature, you have to go ahead and get in units of Kelvin. Okay, so basically you can see in that combined gas law equation, you have 6 variables and one of them we don't know. And it just so happens in this case we don't know T2. That's it. Because you had the second pressure and you had the second volume, but you didn't have the second temperature. So it's very easy to make an algebra mistake. What you're going to see, or what I would do on my, if I was doing it, probably I guess on an answer key, is I would flatten this thing out because I'm going to solve for T2, and I'm kind of, this is like my crisscrossing. I don't know. I would basically flatten it out. I'd have P1, V1, T2 is equal to P2, V2, T1. That's kind of how I learned it. And then I'm going to go ahead and get T2 by itself. So, yep, it's like I said in red a minute ago. You can leave the pressure, those units of millimeters of mercury, that's fine, as long as it's in both states. And you can leave the volume, gosh, it could be in anything. But the temperature, you have to get to the temperature scale that actually has an absolute 0. All right. So then you have to take that, the set of 6 numbers, solve for T2. I kind of showed you how I would cross multiply, okay? And then after you cross multiply, okay, you basically, to get T2 by itself, in that case, you would have to take both sides times 1 over P1, V1. It's all algebra. You have to concentrate. Okay. So I took both sides times 1 over P1, V1. Okay, and so then that left me, that left me T1 or P1, V1, and then P2, V2 along for the ride. Yours might look different. Okay, that's cool. It's the same though, I'm sure. Oftentimes, though, we kind of tidy it up, and you'll see actually kind of these, you'll always have P's, a ratio of P's and a ratio of V's. And that's how it's kind of cleaned up. Okay? So this is the same equation. Okay? Just kind of cleaning it up, putting it P2 over P1 times V2 over V1 times T1. Come on. You just, for whatever of the 6 variables you're missing, you just have to rearrange it. I say just, but I like this version because can you see where the units of pressure are just going to cancel out? They're millimeters mercury, that's fine. And the units of volume are just going to cancel out. They're milliliters, that's fine. So in this case, it looks like this. Okay. P2 over P1 is 353 over 322. V2 over V1 is 46.7 over 33.5 milliliters. And of course, our T1 is 285 Kelvin. So since we're multiplying and dividing, rounding according to 3 sig figs. So the temperature at that second state then has to be 436 Kelvin. And that's it. That's the answer. And we could go ahead, if there's just something reassuring about knocking off units. Like, huh. I can't remember if it said, and I think it did, go ahead and what is the temperature in Celsius. Of course, now we need to subtract 273 from that. Clean it up. We could subtract 273.15, but you get the same answer by the time you round according to the nearest ones, because that's what you were given in the number you want to convert. So 162 degrees Celsius is it. Okay, I think the most common one is, like I said, you have state 1 and state 2, and you're not going to let any gas in or out. So holding N the same. Okay. And sometimes, actually, if you hold the temperature the same, actually, that you're dividing, if you can look at the combined gas law, and actually you're dividing by the same number. So actually, it boils down to this. If the temperature is the same in both cases, you can actually then say if the volume is the same in both cases, okay? And finally, if the pressure is the same in both cases. You don't have to memorize these 3 versions of the combined gas laws because they kind of fall into place. Okay. So here's your assignment slide. And we'll take a look right quick at what they look like. And actually, you're going to see me when I go through them here in a minute. These 3 right here, and these are all due Friday. Okay, but those 3 are the, I'll just put gas law. Okay, then, I can't remember. These next 4 actually have density in them and molar mass. And then last on going over them, oh, I said that wrong, sorry. I wondered how that worked. Anyway, there's really not this overlap with problem 24. Problem 24 is what we just covered. That's where the combined gas laws, where you have state 1 and state 2. And just know that on your final, you are going to run into some of this. Okay, so let's take a look. I know before Thanksgiving, I went ahead and looked at these first 3 problems, and I couldn't find them again. I guess I deleted them. But these were posted, and I'll post them again. This is hints for just your ideal gas law problems. In this case, you're solving for volume. Notice you can find everything else. Okay, and it says you must show all your work to get full credit. Come back. The next one is similar. Really? That's so weird. The next one's similar, so that's 27, 28. Looks like you're solving for pressure. Should be fine. Some of them you don't know what the identity of the gas is, and this you do, and you need to know that it's oxygen or molecular oxygen, O2, because they give you the mass, and you have to use the mass and the molar mass of O2 to get to moles, the N. So, and this is the third of 3. It says don't forget to convert your temperature back to units of Celsius, because of course it's going to give you Kelvin. Okay, so this one then is a little bit different. Let's see if I do this. All right, here's my box. So they give you the pressure. Of course, you got to clean it up, get it from millimeters of mercury to atmospheres. They give you volume. Since you're using the ideal gas law equation, you've got to get from milliliters to liters. They give you the temperature. In this case, they give you, you don't know what the gas is. You don't know what those little particles are, but you know the mass. You know the mass is 0.418 grams. So basically, you have pressure, volume, and temperature. I would knock out those to solve for N, the number of moles. And then once you have N, of course, molar mass of that unknown gas is going to be grams, which you have, 0.418 per mole. And you have the N term. So that's actually how you do the next two. That's 35 and 30, would be 36. Okay, 36 is the same way. What's the molar mass of this gas? Okay. In this case, actually, they give you grams per liter of this unknown gas. And so we've done this before. If you set as your basis 1 liter, and they said the physical constant of this gas is 0.841 grams per liter, then by golly, if that is your volume, which you chose to set, then you know that you have a mass of 0.841 grams. They give you the temperature in Kelvin. You're going to have to look up the relationship, and I think it's a direct 1-to-1, between units of pressure of torr, okay, and millimeters of mercury, or excuse me, atmospheres. It's 1-to-1 for millimeters of mercury, and it's 760 for units between torr and atmospheres. Okay. So then it falls into place kind of like the other one. You're after the molar mass, so if you have pressure, volume, and temperature, you can get to N. Okay, you get N, and then to get the molar mass, you take the grams, which is 0.841, divided by the moles that you got. It's 36. Extra page. Okay, these two are just a little bit different. Okay. They go ahead and they give you, again, the grams per liter. They give you a particular temperature, and they're after pressure. Notice that they're after pressure. You're going to get it in atmospheres from using the R value that we're using. And you're going to want to convert it to millimeters of mercury. Again, since for this, we give you the ID of the gas. Okay, so it's 28.08 grams per mole, because it's 14.00 on the periodic table for nitrogen. So you're given volume, number of moles, and temperature. Okay. You can calculate the pressure then. That's pretty easy. And then one follow-up question, it says, I identified it here as number 2. It says, what is the molar volume under these conditions? So you should have everything you need to knock out the molar volume. And then back to, one more of these. There's 3 of these. This is another density problem. So they give you the density, 2.56 grams per liter. Again, I would take as my base is 1.00 liters. Okay. And it goes on to give you more information. It gives you the pressure in millimeters of mercury. Got to convert to atmospheres. Temperature, convert it to Celsius. Okay. Notice again, you have pressure, volume, and temperature. You can get number of moles, and they're after the molar mass. So you can divide that grams by number of moles. And then similarly, they want the molar volume, and you should be set for that too. And then the first two listed, but the last two we kind of covered. This is just one of those P1 V1 over T1 is equal to P2 V2 over T2. Okay. So you have 6 variables and you don't know V2. So you rearrange the combined gas law, okay, and plug in, and that should work just fine. Again, I'll post these, but this one's a little different. I'll tell on myself. It's been a year since I did this and I was in a hurry, so I looked up in the answer key. But you can see in red how it's different, okay? It's different because if you read it a few times, notice that the volume is staying the same, which is awesome, but they're actually adding moles of the same gas between state 1 and state 2. State 1 is 10.00 grams. State 2 is 12.5 grams because they add 2.5 grams, okay? So the way I worked it before, and I think I would do it again, is if we look at the ideal gas law equation, PV is equal to nRT, and we're going to go ahead and hold volume constant, okay, and let N vary. So this is actually how it ends up. P1 over N1 T1 is equal to P2 over N2 T2, okay? And if you read it a few times, you'll see that actually you're solving for P2. So this is all kind of my hint. So notice that you're given mass of an unknown gas. You don't know its identity, so you can't look up its molar mass. You can't go from grams to moles. But you know that moles are always going to be grams divided by a molar mass. Grams divided by some molar mass. It's the same molar mass. It's the same gas. So my suggestion, and I'll go ahead and show you the rest of this whole thing. My suggestion is just to go ahead and keep N as grams over molar mass. And what you're going to see is that common molar mass will actually cancel. You don't need to know the identity of the gas. As long as the gas is behaving ideally, it does not matter. But this actually is the version of the combined gas law equation that you're going to plug into solving for P2. Okay? Alrighty then. That's all I got.